we will study the problem of inference on graphical models. And with graphical models, we'll primarily focus on factor graphs as the primary choice of graphical models. Suppose we have n random variables x1, x2 up to xn, and we have a joint distribution on them which factorizes in this form as is in some set S. Here each xs is a subset of x1 to xn. Then in our notation of factor graph, we would represent this probability distribution by associating a factor with each term in the product. So we will have this n random variables x1, x2 up to xn, and we will have a factor node associated with each term. So f1 might be associated with some nodes, f2 might be associated with some nodes, and so on. Okay. So as a concrete example, if we have three random variables, and we can write it as fa of x1, x2, fb of x2, x3, fc of x3, then the factors can be written like this. And so the problem that we are interested in is inference on factor graphs. So what we mean by that is we are given some joint distribution which can be represented using factor graphs. We want to compute the marginal distributions. So we want to compute Px, which is the summation of x. We're going to marginalize over all variables except x, P of capital X. So capital X is going to be the collection of all random variables in our notation. Little x is one particular one. And you want to do this for any x in the set x1 to xn. So last lecture, we studied the special case of inference on a chain, a Markov, when it's sort of a Markov chain, and we showed that the inference algorithm reduces to what was known as the forward backward algorithm. Today we will study the generalization of this to cycle-free graphs, and we will introduce in particular a popular algorithm called the sum product algorithm. So we consider a cycle-free factor graph. In this graph, it is clear that if we consider any node x any variable node x, it is connected to various factor nodes. The fs is one factor node, these are other factor nodes. Each of them in turn is connected to other nodes in the network. So there is sets fs will be now a root of another subtree whose children where xs will be the descendants, and there will be a product of factors here which will denote by fs of x and xs. Similarly, f1 will be a root of another subtree with x1 as the descendant variable nodes, and f1 of x and x1 will be the product of all the factors in the tree originating at f1. Likewise, x2 and f2 of x, x2, x3 and f3 of x, x3, and so on. So if we define ne of x to be the neighbors of the variable node x, then the joint distribution which factorizes in the product of all the factors in this graph can also be written as the product over the factors in the neighboring nodes times this functions f of x and xs. Here fs of x and xs is the product of factors on the subtree with fs as the root node. Now note that if we want to marginalize with respect to this node x, then we have to sum this expression. So we can interchange the summation and the product. We take the product out first. Now, now here in the inner summation, only the variables xs matter. So we can write this as summation over xs. And what we are doing here is that we are marginalizing with respect to xs. So the fs is going to be the product of all the factors with fs as the root node, and we are summing up over all the descendants in uh, descendant variable nodes xs. So we'll give this a special name. We will call mu of fs to x as xs of fs of x and xs. We can think of this as the message from the factor node fs to the variable node x. So in other words, to summarize, we had fs here, we had the node x was also connected to other factor nodes. Each one of them had their descendants, and there was the product of all the factors with fs as the root, and similarly it was the case with other factor nodes. The message here from fs to x is on this particular edge connecting fs and x, and it is defined using this way. We sum up the product of all the factors associated with fs over the descendants variable nodes in fs. So we'll now develop, we will a way to compute mu of fs to x recursively. So fs is connected to x. Now in turn, because the graph is cycle free, fs will have its own unique descendants, which will not be shared by any other factor nodes. So we have x1 here, we have x2 here, x3 here, and so on. Now x1 will be a root. It will be connected to a bunch of factor nodes that will in turn be connected to variable nodes. And we will denote by G the product of all the factors with x1 as the root variable node. Similarly, G2 of x2, xs2, and gm. So gi of xi, xsi is the product of factors on the subtree with xi as the root node. So let's look at this quantity fs of x and xs. This will consist of the factor associated with fs, which involves x, x1 up to xm, times the product of the descendants, times g1 of x1, xs1, g2 of x2, xs2, up to gm of xm, xsm. So now when we consider mu of fs to x, we are going to sum over xs. This was the definition from the previous page. If we substitute for fs, we have f of x1 to xm times this product, xsi, g of xi, xsi. Okay. Now what we can do is we note that the term here only depends on x1 to xm, so all we need is to sum over x1 to xm of f of x1 to xm, and then we can basically keep the summation over xs here, product over xsi, g of xi and xsi. The next step is to interchange the summation and the product. And if we do that, the product over xsi comes outside, and inside we just have to sum over xsi, because that is the only variable that matters in this summation. So when we will interchange the summation and the product, we still have the outer summation over x1 to xm. Then we have the product over xsi and the summation over xsi of g of x and xsi. Okay. What we will do next is we will define, and this should be xi, right? I should put xi everywhere. Yeah, this is xi. This has to be xi. Now what we will do is we'll define mu of xi to fs as the inner summation. So this is a message from variable node xi to the factor node fs. And so what we have now is that there is a factor node fs connected to x1, x2, all the way up to xm. What we are sending here is mu of x1 to fs, mu of x2 to fs, all the way up to mu of xn to fs. And then using this, we can use this information to send a message from fs to the variable node x of interest. And the relation we have is that mu of fs to x is the summation of fs of x1 to xm times the product of I going from 1 to m, mu of xi to fs of xi, where we sum, and there should also be an x here, which I missed. The summation is over x1 to xm. So this is the message from factor node fs to the variable node x. This is the message from the downstream variable nodes xi factor node fs, and this is the factors node fs itself. So the point here is that given the messages coming from the downstream variable nodes of fs, we can combine them using this particular relationship to send a message from the factor node fs to the variable node x. So next we need to compute a way for this mu of xi to fs, the message to of a formula to compute the messages from the variable nodes to the factor nodes. So let's look at one such node. Let's consider the node xm. Now xm is connected to a factor node Fs, and we want to compute mu of xm to Fs of xm. In turn, xm is also connected to many other factor nodes. So let's consider fm1, fm2 up to fml. Okay. The factor nodes are connected to downstream variable nodes, and they will have factors fm1, fm2, fm, this is L, connected to them, and we will have messages coming into each variable node. So we will have mu of fm1 to xm, mu of fm2 to xm, all the way up to mu fml to xm. Now clearly the g function we had here in this formula, this is the product of factors in the downstream variables with xm as the root. So if you look at gm of xm and xs, this will be the product of k going from 1 to L, fmk of xm and xmk in this notation. So xmk are the variables in the tree with fmk as the root. Okay, so this is fm1 xm xm1, fm2 xm xm2, and so on. So we have to take the product of all the downstream variables. So gm is the product of factors with xm as the root in the downstream variables, so we just multiply them across the factors. So what we have to do to compute mu of xm to fs of xm, we have to sum gm of xm and xsm over all the downstream variables xsm. So this is the summation of the product of fmk, xm, xmk. So again we interchange the product and the summation, and when we bring the product inside for the kth term, only the variables xmk come into the summation. But remember, this is again by definition marginalizing the downstream variable nodes with fmk as the factor node, and according to our previous definition, this will be the message from the factor node fmk to the variable node xm. So what we have shown is that we now have formulas for computing the message from the variable node xm to the factor node fs. To do that, we just take the incoming messages into this variable node from the downstream factor nodes fm1, fm2 to fml and multiply them in this fashion. To compute the message from a factor node to the variable node, we have this formula. We take the product of all the incoming messages from different variable nodes into the factor node. We multiply with a term involving the factor node and marginalize with respect to all the variables except the variable x of interest. So now we can use this to basically recursively compute all the messages in the network. So let's do the summary now. If we want to compute the message from a variable node, or actually let's do factor to variable first. From factor node to variable node. So in other words, if fs is the factor node, it's connected to x, which is the variable node, then we want to compute mu fs to x. The way it works is we look at all the other variable nodes connected to this factor node. We look at mu x1 to fs of x1, mu x2 to fs of x2, up to mu xm to fs of xm. Then what we have to do is we have to multiply all these incoming messages along with the function associated with fs. So we take fs of x, x1 to xm, and multiply them with, say, j equals 1 to m, mu of xj to fs of xj, and we sum over x1 to xm. This is the message from fs to x at point x. In other words, we multiply all incoming messages, or we multiply incoming messages from all neighboring nodes except node x, for which we want to send the message, multiply with the factor fs, and we marginalize over all variables except node x. Now if we consider the second part, we want to send the message from variable node to the factor node. We will replace the sequence, like we will use the other part of our derivation. So here we have some variable node xm, and we want to send a message to the factor node fs. What we do is, we look at factors connected to it. Should be m1, fm2 to fmk, and we will have messages coming from these factor nodes to the variable nodes, mu fm1 to xm of xm, mu fm2 to xm of xm, mu fmk to xm of xm. And all we have to do here is to compute mu xm to fs of xm. We will just multiply the messages from all the other factor nodes. And so we multiply the messages of all incoming factor nodes except the node fs. So here are now finally the steps we need to compute px. Take x as the root node, start at leaf nodes in the tree or in the factor graph. If the leaf node is a factor node, it has a single parent node x, and what you do is that you set the message from f to x to equal fx. If the leaf node is a variable node, then what you do is you set all the outgoing messages to equal 1 for all factors in the neighboring set, all the neighbors of x. And the next step is to recursively propagate the message from leaf node to root nodes, that is, every node sends message to its parent nodes once it receives message from the children nodes. So the idea again is that for any node x, you will have a bunch of factor nodes which would again be having a bunch of descendants. And basically the probability at node X is going to be the product of the message received from all the factor nodes that are connected to it. And this algorithm is called the sum product algorithm, which allows exact inference on cycle-free factor graphs. Now, if you want to compute for each node X, then the algorithm can be easily tweaked. We arbitrarily designate one variable as a root node. We propagate upstream from the leaf node to the root nodes. The root node upon receiving the message from its children sends the message back to its children, and we propagate messages now downstream all the way to leaf nodes. We have a variable node X here, and if we have factors like this, then we will be sending the messages like this. These are the upstream messages. And we'll also have downstream messages. Once node X has received all the messages from all its neighbors, it will be sending messages itself